In the warm western Pacific, a quiet cluster of storms suddenly explodes into the most powerful typhoon on Earth. Winds of 185 miles per hour, pressure crashing to 890 millibars, a perfect, spiraling eye locked onto a tiny American island. Tonight you'll see the rapid intensification that shocked forecasters, the wall of water that swallowed Saipan, and the ripples Sin Laku punched into the edge of space. If you love stories like this, hit subscribe so you never miss one. Take a deep breath. We begin. On the morning of April 8, 2026, a loose cluster of thunderstorms drifted west of a tiny island called Chuuk. Nobody on the island looked up at it. Nobody on the news mentioned it. It was the kind of weather that happens in the tropical Pacific almost every single week of the year. A satellite passing overhead caught the first image. A swirl of clouds, ragged at the edges. No defined center, no real shape. Forecasters at the Joint Typhoon Warning Center in Hawaii gave it a label and a low chance of development. A small note in a long daily report. Nothing more. But the ocean underneath was already loaded. For weeks, the western Pacific had been baking under unusually warm skies. The water temperature near the equator had climbed past 86 degrees Fahrenheit. That sounds like a nice swim. For a storm, it is rocket fuel. Warm water evaporates faster, lifts faster, and feeds a tropical system the way coal feeds a furnace. Picture a campfire. A small flame on dry kindling looks harmless until you notice the woodpile next to it stretches for miles. The disturbance west of Chuuk was the flame. The Pacific was the woodpile. By the next satellite pass, something had changed. The cluster of storms was rotating. Slowly, almost lazily, but in a clear circle. A column of warm, moist air had begun to rise from the sea surface, drawing in more air from every direction around it. The air rushing in had to spin because the Earth was spinning underneath it. A tropical disturbance had become a tropical depression. Forecasters bumped up the development chance. They started running computer models. Every model agreed on one thing: this system was going to grow. They disagreed on how fast and how big. Some said a tropical storm by the weekend, some said a typhoon by Sunday. A few outlier models suggested something stranger. They showed the system reaching the strongest category on the scale within 4 days. Most forecasters dismissed those outliers. April is supposed to be a quiet month in the Pacific. The big monsters come later, in August and September, after the ocean has been heated all summer. But the ocean was already hot in April, and nothing about that was normal. On the islands of Guam and Saipan, life carried on as usual. Tourists swam at the beaches, schools held morning classes, fishermen checked the forecast and saw a small note about a distant disturbance and went out anyway. The system was hundreds of miles to the south, moving slowly. There was no warning, there was no reason for one, yet. The new storm was given a name from a list of names cycled through every few years. Sin Laku. The word comes from the language of Kosrae, a small island in Micronesia. It means a goddess of nature, of breadfruit, of growing things. It is a peaceful name. It would not stay peaceful for long. Within 36 hours of being noticed, Sinlaku had a clear circulation, a defined center, and steady winds. It had crossed every threshold needed to become a tropical storm. The forecasters watching the next satellite image leaned closer to their screens. Something inside the storm was shifting. The eye was about to open. And once an eye opens over water this warm, the rules of normal weather stop applying. By midnight on April 10th, the swirl west of Chuuk had a new face. The Japan Meteorological Agency upgraded it to a tropical storm and gave it the name on the list, Sinlaku. A few hours later, the storm crossed the next threshold. Sustained winds reached 74 miles per hour. By international agreement, that single number changes everything. A tropical storm becomes a typhoon. Most storms take days to make that jump. Sinlaku did it in roughly 12 hours. Forecasters at the Joint Typhoon Warning Center watched the change happen on infrared satellite images, updated every 2.5 minutes. The cloud tops were getting colder. Colder cloud tops mean stronger updrafts. Stronger updrafts mean the storm is pulling more energy out of the ocean below. On the screen, it looked like the storm was breathing faster and faster. A meteorologist on duty that night later described it as watching a balloon being inflated by a fire hose. The pressure in the center was falling almost too fast to track. Every time the satellite refreshed, the number was lower than the model predicted. This is the moment the technical phrase rapid intensification gets used. The official definition is simple. A storm's winds must increase by at least 35 miles per hour. In 24 hours, Sinlaku blew past that benchmark like it was standing still. By the morning of April 11th, the wind speed had climbed by more than 60 miles per hour in a single day. What does that look like from the ground? Imagine standing on the deck of a fishing boat. At sunrise, the wind is strong but manageable, the kind of breeze that fills a sail. By sunset, the same wind is ripping the sail off the mast. That is what happened over the open Pacific. Anyone caught in the path went from rough seas to survival mode in less than a working day. A weather buoy near the storm's path recorded wave heights that climbed from 10 feet to over 40 feet in a few hours before the buoy stopped reporting. Buoys do not usually stop reporting. The ocean was so violent the instrument simply could not keep up. On Guam, 600 miles to the north, the sky was still blue. The forecast bulletins changed tone overnight. The first emergency briefings began. Officials started talking about possible evacuations. Hardware stores in Hagåtña, the capital, ran out of plywood by lunchtime. Gas station lines stretched around corners. People who had lived through Mawar in 2023 knew exactly what was coming. Inside the storm, something else was forming. A clear, cloud-free hole at the very center. The eye. Most tropical storms never form a true eye. The fact that Sinlaku had built one so quickly was the clearest possible signal. The structure was perfect. The energy was endless. The storm was no longer growing the way most storms grow. It was about to detonate. The forecasters had a saying for moments like this. The storm has gone vertical. It means the engine has fully lit, the chimney is open, and there is nothing in the atmosphere strong enough to push back. The next satellite image would show something none of them had expected to see in April. A storm so symmetrical, so tightly wound, that it looked carved by hand, and the ocean underneath was about to give it everything left in the tank. To understand why Sinlaku grew so fast, look down. Not at the clouds, not at the wind, but at the water. Tropical storms run on heat. They are giant heat engines. They reach down into warm ocean water, pull up evaporated moisture, lift it high into the cold upper atmosphere, and release the energy as the moisture turns back into rain. The warmer the water, the more fuel the engine has. The cycle repeats faster and faster. A storm with cold water under it dies. A storm with warm water under it grows. 80 degrees Fahrenheit is the basic threshold. Below that, tropical systems struggle. Above that, they can intensify. In April of 2026, the surface of the Western Pacific where Sinlaku formed was running close to 87 degrees. That is hot tub territory. But the surface temperature is only half the story. What really matters is something called ocean heat content. This measures how deep the warm layer goes. A thin layer of warm water sitting on top of cold water gets stirred up by a storm, and the storm cools its own fuel. A thick layer of warm water reaching dozens of meters down keeps feeding the engine no matter how hard the storm churns. In April, the warm layer beneath Sinlaku's path was unusually deep, hundreds of feet of warmth, all the way down. A scientist looking at those readings said the ocean had a fully loaded fuel tank, when most years it has a quarter tank. Picture a kitchen pot of water on a stove. When the burner is on low, you can stir the pot all you want and the surface stays cool. Crank the burner to high and pile in more water, and it does not matter how much you stir, the heat keeps coming. The Pacific in April was a stove on high. Why was it so warm so early? Several reasons combined. The previous La Niña pattern, which usually pushes warm water westward, had left the western Pacific stacked with heat. Global ocean temperatures had reached record highs through 2024 and 2025. That heat does not disappear in winter. It gets stored deep in the ocean and slowly comes back up. The result was a setup that should have been impossible in early April. Forecasters knew the conditions favored intensification. They did not realize how favorable. The storm responded immediately. The pressure inside Sinlaku began to fall like a stone dropped down a well. Pressure is the most reliable measure of a storm's true strength. The lower the pressure, the more powerful the system. Standard sea level pressure is about 1,013 millibars. A strong typhoon might dip to 940. Sin Laku dropped past 940 in a matter of hours and kept falling. Below the storm, the ocean was responding too. The water was being pulled up into the engines so fast that satellites could measure a small dome forming at the surface, a bulge of water beneath the eye. The same physics that lifts liquid up a straw was lifting the Pacific itself. Forecasters started running new model scenarios. The numbers coming back were ones nobody wanted to read out loud. A Category 5 by the next morning. A peak strength among the rarest storms ever observed. And the warm water under Sinlaku stretched all the way to the Mariana Islands. Whatever the storm became out here, that is what would arrive at Guam. The fuel tank ran straight to the target. In a quiet office on the island of Oahu, screens covered an entire wall. Each screen showed a different angle on a single point in the western Pacific, infrared satellite imagery on another, pressure trend graphs, wind shear maps. The Joint Typhoon Warning Center is the United States military and civilian forecast hub for the Pacific. On the night of April 11th, the entire room was focused on one storm. A meteorologist rolled her chair forward. The latest pressure estimate had come in, 920 millibars. 20 minutes earlier, the estimate had been 930. A drop of 10 millibars in 20 minutes is a drop most storms never make in a full day. She called out the number. The room went quiet for a beat. A storm's central pressure is the gravity of its strength. As the engine pulls air upward, less air remains at the surface. That falling pressure shows up on barometers as a number going down. The lower it goes, the more air is being moved. A reading of 920 puts a storm in the elite tier. A reading below 900 puts it among the strongest storms ever recorded anywhere on the planet. Sinlaku reached 896 millibars by the time forecasters could compare against historical records. Then it fell again to 890. To find a Pacific typhoon with a lower reading, you have to go back through the records of every storm in the last 70 years and pick out a small handful. The team began working through what they call the rapid update cycle. Normally, a storm bulletin goes out every 6 hours. A rapidly intensifying system means more frequent updates. Every 3 hours, every hour. The team was writing warnings as fast as they could read new data. The technique they relied on is called the Dvorak method. It is a system invented in the 1970s by a meteorologist named Vernon Dvorak. The idea is to look at the pattern of clouds in a satellite image and assign a number based on shape, symmetry, and the temperature of the cloud tops. The colder and more symmetric, the higher the number. The higher the number, the stronger the storm. Sinlaku was hitting numbers most forecasters had only seen in textbooks. A senior analyst pointed at the screen. The eye was not just visible, it was perfectly round, symmetrical down to the pixel. The eyewall, the ring of clouds around the eye, was a complete unbroken circle. The cloud tops were colder than -113 degrees Fahrenheit. The storm had reached what meteorologists call peak organization. There was nothing in the structure that could be improved. Then came the harder conversation. What number to put in the official warning? The Saffir-Simpson scale used by the United States caps out at Category 5. Anything with sustained winds above 157 miles per hour qualifies. Sin Laku was already there. The actual sustained wind speed was estimated at 185 miles per hour, that is, over 25 miles per hour above the threshold. The forecaster typed the warning: Super Typhoon, Category 5 equivalent, track aimed directly toward the Mariana Islands. Estimated landfall in less than 2 days. She hit send. Across Guam and Saipan, emergency phones lit up. The warning was now official, and the storm was still strengthening. The image came down from a satellite called Suomi NPP at 3:30 in the morning Universal Time. A polar orbiting craft built by NASA and the National Oceanic and Atmospheric Administration. Its job is to photograph weather day and night using a sensor that can see invisible light and infrared. When the image rendered on the screens at NASA's Earth Observatory, several scientists stopped what they were doing. In the center of the storm was an eye so clear, so dark, and so perfectly round that it looked drawn with a compass. The walls of cloud rising around it were uniformly bright, uniformly thick. The spiral arms reaching out from the eyewall extended for hundreds of miles in every direction, curving in a smooth and unbroken pattern. This is what a tropical cyclone looks like when it has fully matured. Every part of the engine is firing at the same speed. Every input matches every output. The structure is in balance with itself. Storms with this kind of appearance have a name in the meteorology community: annular. It comes from the Latin word for ring. An annular storm has fewer outer rain bands than a typical typhoon. Most of the energy is concentrated in a thick, symmetric inner ring. These storms are rare. They tend to be among the strongest ever observed. They also tend to weaken slowly because their structure is so stable. Sinlaku was now in that elite category. Picture a flat plate with a perfectly round hole in the middle, the rim of the hole built up like a wall. Now imagine that plate spinning. The outer edge moves slower than the inner edge. The wall around the hole is moving fastest of all. That wall is the eye. Inside the eye there is no rain, no wind, only blue sky and calm air. The strongest winds on the planet are happening just a few miles away from that calm. Standing in the eye of a typhoon is a haunting experience. Sailors and pilots who have been there describe a sudden and total silence after hours of howling chaos. Birds sometimes get trapped inside the eye, riding it for days because the moment they fly outside the eye wall, they are torn apart by wind. The center of a storm is the safest place in it and the most surrounded by violence at the same time. Sinlaku's eye measured roughly 20 miles across. From space, it looked like a deep blue pupil staring up at the satellite. The camera saw straight through it to the ocean far below. The temperature inside the eye wall told the rest of the story. Cloud tops over 50,000 feet up registered colder than negative 110 degrees Fahrenheit. Air that cold, that high, means the storm was lifting moisture nearly into the stratosphere. The energy released when that moisture froze and condensed was the equivalent of dozens of nuclear weapons going off every second. None of it explosive, all of it converted into wind and rain. A scientist at the National Hurricane Center later said the imagery was the most textbook perfect Category 5 he had ever seen. Every rapid intensification case study for the next decade would point back to this moment. Sin Laku had reached the highest possible tier. But the storm was not done. There was one more transformation coming, and the next chapter in the storm's life would put ripples in the upper atmosphere itself. Rapid intensification is one of the most studied phenomena in atmospheric science. It is also one of the least understood. Every forecaster knows the signs. Few can predict exactly when it will happen. The official definition is dry. Sustained winds must increase by 35 miles per hour or more in 24 hours. Sinlaku increased by more than 70 miles per hour in the same window. It doubled the threshold. Storms that grow this fast are called explosive. What makes a storm explode? 3 ingredients have to line up. First, ocean heat content. Sin Laku had it. Hundreds of feet of warm water reaching down beneath the surface, ready to feed the engine without ever cooling. Second, low wind shear. Wind shear is the difference in wind speed and direction at different heights of the atmosphere. High shear tears a storm apart by pushing the top one way and the bottom another. Low shear lets the storm grow straight up like a chimney. In April 2026, the shear over the Western Pacific was almost non-existent. The storm had a clear vertical lane. Third, moist air at every level. Dry air sneaking into a storm from the sides can choke it. Sin Laku was wrapped in a thick blanket of humidity, reaching from the surface to 50,000 feet up. Nothing dry could touch it. Combine those 3 ingredients, and a tropical system can do something that looks almost biological. It pulses, the eye contracts, and tightens. The cloud tops climb higher. Every cycle pumps more heat upward and pulls more moisture inward. Each round leaves the storm stronger than the last. Hour by hour, the engine compounds itself. A simple way to picture it. Imagine pushing a swing. The first push gets a small motion. If you time the next push exactly right, you add to the motion. After a few well-timed pushes, the swing reaches the height of the swing set. After a few more, you cannot push harder without flying off. A storm in rapid intensification is a swing being pushed perfectly every cycle by every part of the atmosphere around it. There is no outside force slowing it down. Climate research has tracked rapid intensification events for decades. The trend is troubling. As ocean temperatures rise globally, more storms are doubling their strength in shorter windows. In the 1980s, fewer than 10% of major hurricanes underwent rapid intensification. Recent years have pushed that number above 20%. The pattern is statistical, not anecdotal. Warmer water makes faster monsters. Sin Laku is now part of the dataset forecasters will study for the next decade. The storm went from a tropical storm to the planet's strongest cyclone of the year in under 3 days. Every model run, every satellite pass, every drop sonde will be replayed and analyzed. The harder question is what happens next time. Forecasters used to give residents of vulnerable islands days to prepare. Rapid intensification cuts that window to hours. A storm that looks weak on Monday can be a Category 5 by Wednesday. That changes how warnings are issued, how evacuations are run, how lives are saved. For Guam and Saipan in April 2026, the window was already closing. The storm had matured. The track was set. The next phase would not be about how strong Sin Laku could get. It would be about where the storm would land and what would be left when the eye passed. The Pacific typhoon season has no official start or end. Storms can form any month of the year. In practice, the Western Pacific produces almost all of its tropical cyclones between July and November. April is supposed to be a quiet month. Most years see 1 or 2 weak tropical storms in April, none of them serious threats. Sin Laku broke that pattern. The storm reached Category 5 strength on April 12th. The list of typhoons that have ever reached that level in the months of January through April is short. Climate scientists at Yale Climate Connections counted only 10 storms in the historical record. Sin Laku is one of them. Looking at every storm by date, only one ever reached Category 5 earlier in any calendar year. That was Super Typhoon Hester on January 1st, 1953. By wind speed at that time of year, Sin Laku tied with Hester for second place behind Super Typhoon Surigay from April 2021. Surigay topped out at 195 miles per hour. Sin Laku reached 185. Both storms intensified in the same general region of the Western Pacific. Why is April supposed to be quiet? Because the ocean is cooler in early spring. The sun has not yet had time to heat the surface deeply. Wind shear is also typically higher in spring. Storms that try to form often get torn apart before they organize. Sin Laku faced none of those obstacles. The ocean was hot, the shear was low, the moisture was abundant. April 2026 gave the storm the conditions of a peak August environment. Researchers studying long-term trends have flagged this kind of off-season monster as a warning sign. In a warming climate, the windows of favorable storm conditions are stretching. Months that used to be reliably quiet are starting to produce serious systems. The West Pacific is one of the most sensitive regions on Earth to ocean temperature changes. What happens here often shows up later in other ocean basins. Picture a calendar marked with red dots for every Category 5 storm in history. For most of the 20th century, the dots cluster heavily in late summer and early fall. The early months are nearly empty. In recent decades, more dots have appeared in spring. Sin Laku is one of those dots. It is not an isolated case. It is part of a pattern. A meteorologist quoted by Yale Climate Connections noted that the average yearly count of Category 5 storms globally has been increasing since accurate satellite data became available in the early 1980s. The increase is statistically significant. The world produces more of these storms now than it did a generation ago. 2025 saw 5 Category 5s. 2026 already had one before Sinlaku in the South Indian Ocean, called Horacio. 2 Category 5 storms before mid-April. That has happened in only a handful of years on record. For the people of Guam and the Mariana Islands, statistics do not matter once the warning sirens go off. They were about to take a direct hit from a storm that historical climatology said should not exist this early in the year. Their experience would soon become a case study. Their preparation would soon be tested. A senior forecaster summed it up in one sentence during a briefing. The rules are changing. The next chapter would test that statement on the ground. Numbers are easy to read on a screen. They are harder to feel in a body. 185 miles per hour is the maximum sustained wind speed Sinlaku reached at peak intensity. To understand what that number does to the world it touches, you have to translate it into sensations. Start with sound. A typical strong wind, the kind that bends trees, moves at around 40 miles per hour. It sounds like a freight train passing through a forest. Doubling that speed to 80 does not double the sound. It quadruples it. Wind energy increases with the square of the speed. So winds at 185 miles per hour carry more than 20 times the energy of a 40 mile per hour gust. The sound becomes something the human ear was never designed to process. Witnesses of past Category 5 storms describe it as a continuous, deep, vibrating roar that drowns out every other sound for hours. People shouting next to each other cannot be heard. The roar penetrates concrete walls. It rattles teeth. It causes a kind of panic that has been described as primal. The brain does not know what to do with a sound that loud and that constant. Now picture a wall. A standard wood frame house wall is rated to hold against winds in the range of 90 to 110 miles per hour. At 185, the wood frame fails. Nails pull from boards, sheathing strips off. The wind drives debris through the walls like darts through paper. A piece of plywood becomes a flying knife. A roof tile becomes a missile. A fallen tree becomes a battering ram. Every loose object in a wide radius around the storm is now part of the wind. The hazards multiply each other. A car parked on a street can be picked up and moved several feet. A cargo container, which weighs several tons, can be tipped over. Trees do not just bend, they snap. Coconut palms native to the Pacific are flexible by design and can survive winds that would shatter a maple. At 185 miles per hour, even palms break first. The trunks then crack at their weakest points. Whole groves go down within minutes. The water response is just as extreme. Wind-driven waves do not behave like normal waves. At Category 5 strength, waves can reach over 50 feet in open ocean. The spray from those waves is whipped horizontally so violently that visibility drops to a few feet. The salt water mixed into the air corrodes everything it touches within hours. Electrical systems short out. Vehicles seize up. Even buildings sealed against wind let salt mist in through tiny gaps. Now consider air pressure. At Sinlaku's peak, the central pressure was about 890 millibars. The pressure outside the storm was around 1010. The difference is not just numerical. A person inside a sealed building near the eyewall would feel it as a sudden pressure drop, the same sensation as a fast elevator descent or a plane losing altitude quickly. Some people feel it in their ears. Some feel it as a headache. Some feel both. Animals feel it more sharply than humans. Birds become disoriented. Domestic pets often refuse to go outside hours before a storm arrives. Their senses pick up the pressure change before any radar can. This is the world Sin Laku built around itself in the open Pacific. Now that engine of wind, water, and pressure was driving toward land, and the next phase would test what humans had built to withstand it. There is a number on the meteorological record books that gets whispered with respect. It is the central pressure of a tropical cyclone at its strongest moment. The lower the number, the stronger the storm. The list of storms that have ever reached below 900 millibars anywhere on the planet is short. Sinlaku reached 890 millibars during its peak intensity. That places it among the elite few. To put that number in perspective, the average sea level pressure on a quiet day is around 1013 millibars. A passing weather front might bring the pressure down by 10 or 20. A regular hurricane might push the pressure to 960. A major hurricane to 940. A Category 5 down to 920. Below 900 is a different category of phenomenon entirely. These storms are sometimes called extreme tropical cyclones, a term forecasters use only when the regular language runs out. The all-time record for lowest pressure measured in any tropical cyclone is held by Super Typhoon Tip in the Western Pacific in October 1979. Tip reached 870 millibars. Hurricane Wilma in the Atlantic in 2005 reached 882. Hurricane Patricia in the Eastern Pacific in 2015 reached 872. Sinlaku's 890 puts it in the same conversation as those names. Each of them is studied in textbooks. Each one rewrote what forecasters thought was possible. What does a pressure that low actually do? It bends the ocean upward. The atmosphere normally presses down on the sea with a measurable weight. When the atmosphere lightens dramatically in one spot, the water below rises to fill the space. The rise is small but real. For every 10 millibar drop in pressure, the sea surface lifts roughly 4 inches. Sinlaku's pressure deficit was over 120 millibars. That alone lifted the sea beneath the storm by nearly 4 feet before any wind effect was added. That 4-foot dome of water moves with the storm. It is part of what becomes the storm surge when the system reaches a coastline. The wind piles more water on top of it. The shape of the seafloor near the shore can amplify it further. By the time it hits a beach, that initial dome can be the seed of a wall of water dozens of feet high. The pressure also drives the wind. Air moves from areas of high pressure toward areas of low pressure. The greater the difference, the faster the air moves. Sinlaku's pressure gradient was extreme. Air from hundreds of miles away was being pulled toward the eye at speeds that built and built as the air spiraled inward. The fastest winds in the storm were not at the eye itself, but at the inner edge of the eye wall, where the gradient was steepest. Inside the eye, the calm was equally extreme. With pressure that low, the sky above the eye became visible from below in some cases. Witnesses inside past Category 5 eyes have described seeing stars at night through the stadium-shaped opening above them, a circular wall of cloud rising thousands of feet, a clear hole at the top. Some describe it as standing at the bottom of a vertical canyon made of weather. Sin Laku was not just a strong storm. By the measure of pressure, it was one of the strongest storms ever recorded on Earth, and it was now hours from making landfall on inhabited islands. Most storms are not pretty. They are messy, lopsided things with one side stronger than the other, and clouds blowing off in random directions. Looking down at a typical typhoon from a satellite, you see a swirl that looks vaguely like a buzzsaw with chunks missing. Sinlaku looked nothing like that. From orbit, the storm was a flawless wheel. 3 different geostationary satellites had eyes on it at all times. Himawari, 9, operated by the Japan Meteorological Agency. The American goes west, a constellation of polar orbiters passing overhead every 90 minutes. Image after image showed the same shape, a circular eye, a perfectly round eyewall, spiral bands curving outward in even balanced sweeps, cloud tops at the same height across the entire structure. This kind of symmetry is rare. It happens only when every part of a storm is in equilibrium with every other part. The energy flowing in from the warm ocean matches the energy radiating outward at the top. The wind speeds at the surface match the wind speeds at altitude. The moisture content is consistent at every angle around the eye. There are no weak spots, no dry slots, no asymmetric inflow. In meteorology textbooks, this state is sometimes called the steady-state typhoon. It is a theoretical maximum. Most real storms never reach it, because the atmosphere is too messy and the surrounding conditions change too fast. Sinlaku held that state for several hours. Why does symmetry matter? Because a symmetric storm is a more efficient storm. Energy is not wasted on lopsided structure. Every watt of heat coming up from the ocean is converted into wind and precipitation with as little loss as possible. The result is a storm that hits its peak intensity faster and holds it longer than an asymmetric one. It also means the storm is harder to weaken. Asymmetric storms have weak points. Dry air can sneak in through a thin spiral band. Wind shear can tilt a tilted storm even further. Symmetric storms have no entry points. They protect themselves with their shape. Imagine a wheel spinning at high speed. A perfectly balanced wheel can spin for hours with very little energy input. A wheel with a dent on one side wobbles and slows down quickly. Sinlaku was the balanced wheel. Every part was tuned to every other part. The most striking detail in the satellite imagery was the eye wall itself, not just round, but uniform in thickness, all the way around. The vertical wall of clouds surrounding the calm center rose evenly to about 50,000 feet on every side. From above, it looked like a stadium with a circular roof opening. From the side, on rare aircraft observations of similar storms, the eye wall is described as a smooth cylindrical bowl, like the inside of a glass tumbler. Within that eye wall, winds reached their maximum. Forecasters use a measurement called the radius of maximum winds. For Sinlaku, that radius was small, only about 10 miles from the eye's center. A small radius concentrates the strongest winds in a tighter ring. It also means the most violent zone of the storm is very localized. A house 30 miles from the center experiences much weaker conditions than a house 10 miles from the center. Where the eye wall passes, there is no preparation that fully matters. The shape from space told forecasters one more thing. A storm this perfect was at peak strength. It could not get more efficient. Whatever happened next would be a slow journey downward from this peak, but the journey down was still aimed at land, and the next change inside the eye would have life and death consequences. On the night of April 12th, a NASA satellite called NOAA-20 swept overhead in low orbit. Its sensor that night was the day-night band on the visible infrared imaging radiometer suite. The instrument can detect light at extremely low levels, like moonlight reflecting off clouds, or the faint glow of city streets. The image it produced over the Pacific that night went viral within the meteorology community. Above the dark mass of Super Typhoon Sin Laku, the satellite picked up something strange. concentric rings of faint light radiating outward from the storm. The rings were not clouds. They were not lightning. They were not city lights. They were waves of glowing air at the edge of space, 60 miles above the storm, in a layer of the atmosphere called the mesospheric airglow waves. They form when a powerful enough disturbance at the surface punches a column of energy upward through every layer of atmosphere above it. The energy reaches the mesosphere as gravity waves, which are not waves of gravity but waves driven by the gravity-restoring force on disturbed air. They look like ripples on a pond, only the pond is 60 miles above the ocean, and the ripples are made of glowing oxygen molecules. For a storm to produce visible airglow waves, it has to be extremely powerful. Most strong typhoons do not generate detectable patterns. Sin Laku produced ones bright enough to be photographed by satellite hardware designed for very different purposes. A scientist at the Cooperative Institute for Meteorological Satellite Studies in Wisconsin posted the image online with a short caption. The image showed a Category 5 super typhoon at the bottom, and a series of beautiful faint, expanding rings of light reaching outward through the upper atmosphere. Most people on Earth never see the mesosphere. It is too thin for normal aircraft to fly through, and too thick for orbital spacecraft to operate in. It is sometimes called the ignerosphere because so little is known about it. Compared to the layers above and below, the temperature there can drop to -150 degrees Fahrenheit. The air pressure is 1,000th of what it is at sea level. The mesosphere is the highest layer where meteors burn up, and the lowest layer where the auroras occur. For the energy of a tropical cyclone to reach all the way up there is remarkable. A storm that does it has to be extraordinarily intense, with updrafts powerful enough to shove air up through the troposphere, the stratosphere, and into the mesosphere itself. Sin Laku was doing exactly that. The waves told scientists something useful too. The shape and spacing of the rings can be analyzed to estimate the energy output of the storm below by looking at the spacing of the rings and the speed at which they moved outward. Researchers could calculate that the storm was releasing energy at a rate consistent with one of the most powerful tropical systems ever observed on Earth. Picture a stone dropped into a still pond. Ripples expand outward. Now imagine the stone is so large it takes the entire pond and lifts it into ripples that travel for hundreds of miles. That is what Sin Laku was doing to the upper atmosphere. The storm was a stone, the air was the pond, and the ripples were a glowing record of the impact. The image also served as a warning. A storm capable of disturbing the edge of space was about to encounter inhabited islands. The full force of that energy was not aimed at the mesosphere. It was aimed at homes, schools, and harbors a few hundred miles away. The island of Guam sits in the western Pacific, roughly 1,500 miles east of the Philippines and 1,200 miles south of Japan. It is small, 30 miles long, 4 to 12 miles wide. About 170,000 people call it home. It is also one of the most typhoon-prone places on Earth. Forecasters call this stretch of ocean Typhoon Alley. It is the part of the western Pacific where most of the world's strongest tropical cyclones form and pass through. The reasons are geographic and atmospheric. The water around Guam is some of the warmest open ocean water on the planet. The trade winds blow steadily from east to west across the entire tropical Pacific. Storms that form in the eastern part of the basin often cross thousands of miles before they reach the western edge. They have plenty of time to grow. By the time they pass Guam, many are at peak strength. Typhoons in this region tend to move from southeast to northwest. The path puts Guam squarely in the firing line. The island has been hit by major typhoons over and over in recorded history. Karen in 1962 flattened most of the wooden structures on the island. Pamela in 1976 left damage that took years to repair. Paka in 1997 brought wind gusts measured at over 200 miles per hour. Pongsona in 2002 cut power for weeks. And then Mawar in 2023, a Category 5 super typhoon, that came within a hair of a direct hit on the most populated parts of the island. Each of those storms taught Guam a hard lesson, and each lesson became part of how the island was rebuilt afterward. Wood frame construction was abandoned in favor of reinforced concrete. The traditional chamorro houses still stood in some villages, but most of the modern buildings were now built like military bunkers. Steel rebar laced through every wall, hurricane shutters bolted onto every window, generators in nearly every business, water tanks on every roof. Anderson Air Force Base on the northern end of the island and Naval Base Guam on the western coast housed thousands of personnel and billions of dollars in hardware. Aircraft can be flown out before storms arrive, ships can put to sea, but the buildings, the runways, the fuel depots, all of it stays. Each typhoon is a test. The civilian population has lived with typhoons for generations. The Chamorro people are the indigenous inhabitants of the Marianas. Their traditional knowledge of weather patterns is woven into the culture. Children grow up hearing stories from grandparents about storms that came before. Each generation passes down practical lessons: where to shelter, what to stockpile, how to read the sky when the official warning may not arrive. By the morning of April 13th, that traditional knowledge was being put to use again. Families were moving valuables to higher floors. Yards were being cleared of anything that could become a missile. Pets were being brought inside. Cars were being parked away from trees and power lines. The island had been here before, many times, but Mawa in 2023 had been less than 3 years earlier. Repairs from that storm were still visible across the landscape. Some homes had not yet been fully restored. Now another monster was approaching, and the recovery clock was about to reset before it had finished its first run. The forecast track had Sin Laku passing close to Guam, possibly directly over Saipan and Tinian. The window for preparation was closing fast. The next chapter would happen on the airwaves, in the kitchens, and in the sirens that began to sound across the islands. When a typhoon approaches the Mariana Islands, the local National Weather Service office in Tian, Guam, becomes the most important place in the region. The forecasters there run the warnings that reach every household and business across thousands of square miles of ocean and land. By the morning of April 13th, the office had issued its most serious alert in years. A typhoon warning was active for Guam, Rota, Tinian, and Saipan. A separate flash flood watch was in effect for the entire region. Coastal areas were under a storm surge warning. A typhoon warning in this region means destructive winds are expected within 36 hours. The advisory bulletins update every 3 hours during a typhoon event. Every local radio station carries them. Every television station interrupts programming. Every cell phone in range receives a wireless emergency alert. The system is designed so that no one can claim they did not know. Across Guam, life shifted into a familiar rhythm. The schools closed first. Teachers helped students get home. The University of Guam suspended all classes. The hospitals began reviewing their generator fuel and securing rooftop equipment. Police and emergency services moved into 12-hour shifts. The ports stopped accepting new vessels. The airports announced cancellation lists that ran several pages long. Hagåtña, the capital, took on a particular look. Plywood appeared over storefront windows. Sandbags lined doorways in low-lying areas. Concrete barriers were dragged across alleys. Restaurants gave away food rather than risk it spoiling without power. Convenience stores ran out of bottled water. By mid-morning, a line at one gas station stretched for over a mile. In the villages on the southern end of the island, where homes are often smaller and older, residents were directed to one of dozens of designated typhoon shelters. Most were public schools and government buildings designed to withstand Category 5 winds. Each one had been built and tested for exactly this scenario. Buses ran extra routes to bring in residents from outlying areas. Pets were welcomed. Service animals were kept with their owners. A woman named Maria ran a small shop in the village of Inarajan. She had ridden out Pongsona in 2002, Mawa in 2023, and several smaller storms in between. Her routine was practiced. Cans of food and bottled water moved into a back room. The freezer was filled with ice in case the power lasted long enough to keep food cold for a few days. The shutters were bolted at 3 in the afternoon. By 6, she was at a relative's house in a concrete home further inland. On Saipan and Tinian, the forecast track was even more direct. The two islands lie just north of Guam, with smaller populations and fewer concrete shelters. Officials there had been working for 2 days to relocate vulnerable residents. Tourists at the beach hotels on Saipan were being moved to inland buildings. The hospital on Tinian, a small facility with limited staff, was reinforced and fueled for extended operation. On the radio, a forecaster's voice was steady but urgent. The center of the storm was now expected to pass directly over Saipan and Tinian within the next 18 hours. Sustained winds at the eyewall remained near 175 miles per hour. The storm surge could reach over 15 feet on exposed coasts. Anyone not yet in shelter should be moving now. The waves on the south-facing beaches of Guam had already changed. They were larger, more chaotic, and breaking further out from shore. The first signs of the storm were arriving. The full force was hours away. The next chapter would test every preparation. In the early hours of April 13th, something happened inside Sin Laku that forecasters had been watching for. The storm began an eyewall replacement cycle. This is one of the strangest internal processes a tropical cyclone can undergo. A mature storm with a tight, compact eyewall sometimes develops a second, larger ring of intense thunderstorms further out from the center. The outer ring competes with the inner ring for moisture and energy. Eventually, the outer ring chokes off the inner one. The original eyewall collapses. The new outer ring contracts inward and becomes the new eyewall. While this happens, the storm temporarily weakens. The tight, efficient core is broken up. Wind speeds drop. The pressure rises. The structure looks ragged on satellite imagery for a period of hours. For Sin Laku, the timing was critical. The eyewall replacement began as the storm approached the Mariana Islands. By the time the new eyewall fully formed, the storm had weakened from a peak of 185 miles per hour sustained winds down to about 155. Still a Category 4, still catastrophic, but not the all-out Category 5 that had been spinning over the open ocean a day earlier. The new eyewall was also wider than the old one. The radius of maximum winds expanded from about 10 miles to over 20. That meant the most violent zone of the storm was spread over a larger area but was less intense at any single point. The maximum gust at the worst location was lower than it would have been before the cycle began. For the people of Guam, this internal change in the storm probably saved lives. The storm passed close to Guam, but the eyewall did not pass directly over the most populated parts. The island was hit hard, but not at peak intensity. Wind gusts at Guam International Airport reached around 115 miles per hour during the storm's closest approach, damaging but survivable for most reinforced structures. For Saipan and Tinian, the news was worse. The track of the storm carried the new, wider eyewall directly over both islands. They took the full force of the post-replacement Category 4. Wind gusts on Tinian were estimated above 140 miles per hour. The northern coast of Saipan, exposed to the eyewall's strongest sector, was hit by sustained winds in the same range. Eyewall replacement cycles are common in mature tropical cyclones. They are part of the natural life cycle of a strong storm. Forecasters watch for them carefully because they change the timing and the intensity of landfall. A storm that completes a cycle just before landfall often hits weaker than peak. A storm that finishes a cycle and then re-strengthens before landfall can hit even harder than its earlier peak. Sinlaku did not finish re-strengthening. The cycle was still in progress when the eye crossed Saipan. Some forecasters believe a few more hours over open water would have produced an even more powerful storm at landfall. The internal physics of the replacement is still being studied. A leading theory holds that as a storm grows, An outer ring of thunderstorms naturally forms because the original eyewall cannot sustain its tight structure indefinitely. The atmosphere wants to spread the energy out. The cycle is the storm's way of redistributing itself. Picture a campfire that becomes too tall. It splits into two smaller fires nearby, and the original collapses. Each cycle reshapes the storm. Each cycle changes what happens when the storm reaches land. For the people of the Marianas, the cycle was the difference between catastrophe and disaster. Disaster was bad enough. The next chapter would show what disaster looks like on a small island. Saipan and Tinian are sister islands. Saipan is the larger of the two, about 44 square miles, home to roughly 43,000 people. Tinian sits just south of Saipan, about 39 square miles, home to fewer than 3,000. Together, they form the heart of the Northern Mariana Islands, a United States territory. On the night of April 13th and into the morning of April 14th, the eye of Super Typhoon Sinlaku crossed both islands. The first to feel the full force was Tinian. The eyewall arrived just after midnight local time. Within an hour, the wind had risen from a strong gale to a steady scream. Power lines snapped one after another along the island's main road. The lights of San Jose, the largest village, went dark in successive blocks. Anyone still outside was driven indoors by flying debris. The rain came down in sheets, so dense they reduced visibility to near zero. Roof tiles peeled off in the wind. Older wooden homes lost shingles and then sheathing. The sound described by survivors was a continuous roar, overlaid with the cracks of breaking trees and the screech of metal being torn from frames. About 2 hours later, the eye reached Tinian. For perhaps 30 minutes, the wind dropped to almost nothing. The rain stopped. People in shelters who had cell signal stepped outside to check on their homes. Some described looking up at a circular wall of cloud rising thousands of feet. Clear sky directly above. The moon barely visible through high atmosphere haze. Then the backside of the eyewall arrived. The wind reversed direction. Anything that had been weakened but not destroyed in the first half of the storm now took the second half from the opposite side. Many roofs that had survived the initial blow gave way during the back-end winds. The damage doubled in the second hour. By the time the storm cleared Tinian and moved north over Saipan, the smaller island looked transformed. Hundreds of homes had lost roofs. The harbour was littered with debris. Fishing boats had been thrown ashore. Several were total losses. The airport runway was strewn with tree branches and metal panels from hangars. Saipan caught the eyewall a few hours later. The storm had not weakened in the brief crossing. The same pattern played out on a larger scale. The capital village of Garapan flooded as storm surge pushed seawater up the coastal streets. The airport recorded over 5 inches of rain in less than 24 hours, a top 10 wettest day in the island's history. Power went out across the entire island within minutes of the eyewall's arrival. A teacher named Joseph rode out the storm with his wife and 2 children in the bathroom of a concrete house in the Cagman neighborhood. He described the experience in a later interview. The walls held. The roof held. But the noise was constant and oppressive for 3 hours. His youngest child cried through most of it. His wife held a flashlight to keep the bathroom lit. When the power went, they prayed together. When the wind finally began to slow, his first action was to step into the hallway and find that all the windows in the rest of the house had blown in. Sand, leaves, and shredded curtain pieces covered the floor. Across both islands, the death toll began to be counted, 12 people in total, some from collapsing structures, some from flying debris, some from drowning in floods. The number could have been higher. Most residents had heeded the warnings. Most had been in proper shelters. The next chapter would show what came after the wind stopped. Storm surge is the deadliest part of most tropical cyclones. More people drown in surge than die in wind. Sin Laku produced a surge unlike anything the Marianas had seen in decades. The mechanism behind storm surge is straightforward. A tropical cyclone has very low pressure at its center. The sea responds to that pressure drop by lifting upward. Add wind blowing across the water, and the wind pushes the lifted water in front of the storm. When the storm reaches a coast, the water has nowhere to go. It piles up against the land. The shape of the seafloor near shore can amplify the effect. A gentle slope causes the water to rise high. A steep drop-off lets it dissipate. For Sin Laku, the pressure deficit alone lifted the water beneath the storm by about 4 feet. The wind effect added several more feet. By the time the surge reached the western coasts of Saipan and Tinian, it was estimated at over 15 feet above normal high tide. A 15-foot wall of water hitting a low-lying coastline is catastrophic. Single-story homes are submerged. Cars float and become battering rams. Coastal trees are uprooted. Entire stretches of beach are reshaped overnight. Survivors in the village of Tanapag on Saipan described the surge as a slow-moving flood that arrived in pulses. Each wave carried more water inland than the last. By the time the peak surge hit, the water was up to the eaves of single-story homes. Anyone caught at ground level had to climb to upper floors or rooftops to survive. Mangrove forests, which once buffered some coasts, had been thinned out by previous storms and coastal development. Where mangroves remained, they slowed the surge. Where they did not, the water came in unchecked. The surge also brought salt water deep inland. Soil that had been productive farmland became sterile in some areas. Wells became contaminated with salt and could not be used for drinking water. The cleanup of these inland salt flats would take weeks. A particularly cruel feature of storm surge is timing. The peak surge usually arrives near the time of peak wind. People who might otherwise try to evacuate by car or boat cannot do so safely. The combination of high water and high wind traps anyone who has not already moved to high ground. The surge also carries debris, tree trunks, lumber from destroyed buildings, propane tanks, vehicles. All of it floats in the rising water. The massive moving debris adds to the force of the surge. A wooden beam striking a house wall at 5 miles per hour can punch through. A propane tank can rupture and ignite. The surge is not just water, it is a soup of dangerous objects moving in formation. In the harbour of Saipan, dozens of small boats broke their moorings during the storm. Some sank. Others were thrown into other boats or onto the docks. A few were carried hundreds of yards inland by the surge and deposited on streets and in yards. Photos taken in the days after the storm showed fishing boats sitting in the middle of intersections, far from any water. Storm surge prediction has improved dramatically in recent decades. Computer models can forecast the height and timing of surge with reasonable accuracy. Warnings now include specific surge values for specific coastlines. The forecasts before Sin Laku had been accurate. The surge that hit was within the predicted range. But knowing the surge was coming and surviving it are different things. The next chapter would look at the rain, which came down in volumes that turned the islands into temporary lakes. While the wind broke buildings and the surge drowned coasts, Sinlaku had one more weapon: rain. In a 24-hour period spanning April 13th and 14th, Guam International Airport recorded just over 9 inches of rainfall. Saipan International Airport recorded nearly 6 inches in the same window. Both totals placed the day among the wettest in each island's history. To put these numbers in perspective, an inch of rain dropped over an acre of land equals about 27,000 gallons of water. 9 inches over the same acre equals nearly 240,000 gallons. Multiply that across an entire island, and the volume of water dropped during the storm runs into the billions of gallons. The land cannot absorb water that fast. Tropical soils, especially those that have already been wet from rain in the days before a storm, reach saturation quickly. Once saturated, every additional inch of rain runs off the surface. It flows downhill in sheets, gathering speed and volume as it goes. On Saipan, the central highlands sent runoff cascading down toward the coast. Streams that are normally dry or barely flowing turned into torrents in minutes. Rural roads became rivers. Bridges over small drainages were overtopped or washed out entirely. Vehicles caught on flooded roads were swept away. The flooding interacted with the storm surge in complicated ways. Where rain runoff met incoming surge, the water levels rose even higher than either flood would have produced alone. In low-lying areas behind beachfront, the water from inland and the water from the sea met in the middle and turned neighborhoods into temporary lakes 10 or more feet deep. On Guam, the southern villages were hit hardest by flooding. The mountainous terrain in the south channels rainwater into a network of small rivers. During Sin Laku, every one of those rivers ran above flood stage. The Talafofo River, normally a slow-moving waterway, became a brown foaming torrent that overtopped its banks and spread across surrounding farmland and homes. A farmer in the Talafofo area lost more than 50 chickens, 2 pigs, and most of his crop in a single night. The water rose so fast, he and his family had time only to move themselves to higher ground. The animals in their pens could not be reached safely. The crop in the field was gone in hours. Landslides became a serious threat by the second day. Saturated soil on hillsides loses its grip. Trees, brush, and rocks slide downhill in unpredictable directions. Several homes built on hillsides on Saipan were damaged by mudslides. One family had to be rescued by emergency crews from a home that had partially slid down a slope. The runoff also carried debris into the ocean. Brown plumes of muddy water extended for miles offshore on satellite imagery, captured after the storm cleared. The plumes contained soil, fertilizer from farmland, sewage from damaged systems, and chemicals from flooded buildings. Coral reefs near the affected coasts faced a wave of pollution that could damage them for years. Drinking water systems were overwhelmed. Treatment plants on both islands lost power, and intake systems were clogged with debris. For days, residents had to rely on bottled water trucked in from emergency supplies, or boiled tap water once power was partially restored. The rain also fell on damaged buildings. Homes that had lost roofs during the wind phase took on water during the rain phase. Belongings that survived the wind were ruined by the water. Insurance adjusters in the weeks that followed noted that many claims included damage from both phases. The combination cost more than the wind alone would have. The next chapter would look at the saturated hillsides and the slow, dangerous slides that followed. Records have a way of being broken in eras of warming oceans. On April 14, 2026, Saipan International Airport added one more entry to its top 10 list. 5.73 inches of rain fell in 24 hours. That number does not sound impressive at first. A heavy spring rain on the United States mainland can drop similar amounts, but on a small Pacific island with steep terrain, soil already saturated from days of pre-storm rain bands, and infrastructure already stressed by the wind, every additional inch is amplified. The morning after the eyewall passed, satellite imagery captured a remarkable scene. Saipan looked like a green island streaked with brown lines. Each line was a stream or gully running full and overflowing. The coastlines on the leeward side were ringed with a wide brown halo of sediment-loaded runoff entering the lagoon. The capital village of Susupe sits on a flat stretch of land between the western beach and a freshwater lake called Lake Susupe. During the storm, the lake rose several feet. The streets between the lake and the beach turned into a single broad sheet of water. Cars left in driveways were partially submerged. Lower floors of homes took on a foot or more of water. Office buildings on the main road through Susupe lost ground floor furnishings to flood damage. Garapan, the busiest tourist district on Saipan, fared no better. The drainage system there had been upgraded after Sudala in 2015, but the upgrades were designed for storms that drop 2 to 3 inches in a day. Sin Laku doubled that amount. The drains backed up. Storefronts on the main strip flooded. A souvenir shop owner reported losing every item on her ground floor shelves, within a single hour. In the rural village of Tanapag, the situation was worse. The village sits at the mouth of a small river. During the storm, the river ran higher than anyone present had seen in their lifetime. A family that had lived in the same house for 40 years told reporters they had never seen water reach the porch. On the night of the storm, the water reached the bedroom windows. Schools across the island, which had been used as shelters during the storm, became staging grounds for relief operations afterward. Volunteers passed out bottled water, dry clothing, and basic supplies. Local restaurants that had power from generators offered free meals to anyone who needed them. The community response was immediate and organized. The rainfall numbers also told a story about climate trends. Warmer air holds more water. For every degree Celsius the atmosphere warms, it can hold roughly 7% more moisture. That extra moisture has to come down somewhere. Tropical cyclones in warmer climates tend to produce heavier rainfall. Studies of recent typhoons show a measurable increase in rainfall rates compared to similar storms decades earlier. Sin Laku fit the pattern. The storm dropped more rain in a day than most April typhoons of the past would have produced. The combination of heavy rainfall, high winds, and storm surge multiplied the damage in ways that would not have happened with any one of those factors alone. A retired meteorologist on the island summarized it in a single sentence to a local reporter. The storms are not coming more often, but they are doing more when they come. The water that fell on Saipan eventually had to drain. As it did, it carried soil, debris, and pollution into the surrounding sea. The reefs offshore would feel the impact in the weeks that followed. The hillsides that gave up the runoff faced a different threat. Saturated slopes do not always stay where they have always been. Some of them were about to move. The hills of Saipan and Tinian look stable on a normal day. Volcanic in origin, covered in tropical brush and small trees, they have stood for thousands of years. After Sin Laku, several of them did not stay standing. A landslide is a simple piece of physics with complicated outcomes. Soil holds itself in place by friction between its particles. Water sneaking into the gaps reduces that friction. When enough water enters, the friction drops below what gravity demands, and the soil starts to move. The bigger the slope and the wetter the soil, the larger the slide. After Sin Laku, the soil on every hillside in the affected islands was completely saturated. Days of pre-storm rain bands had wet it down. The eyewall rains had soaked it through. Many slopes were holding more water than they ever had before. The first major slide on Saipan happened in the village of Capitol Hill, where the seat of the local government is located. A section of slope behind a residential block let go in the early morning hours after the storm. Mud, brush, and rocks slid downhill into the back of 3 homes. The residents had been evacuated to a public shelter. Their homes were not so lucky. 2 were destroyed. The 3rd was damaged beyond repair. A more dramatic slide occurred on Tinian, where a cliff above a beach gave way and reshaped the shoreline. The cliff had been considered stable. The slide deposited several thousand tons of material at the base of the cliff and into the water. A small access road that ran along the cliff was buried. Smaller slides happened across both islands in the days following the storm. Each one was a hazard to anyone trying to clear roads or restore utilities. Crews working on power line repairs in the southern hills of Saipan had to stop work multiple times when small slides came down without warning. The risk continued for days after the rain stopped. Water that had soaked into hillsides during the storm took time to drain out. Even on sunny days, the slopes remained dangerous. Local officials issued ongoing warnings. Anyone walking near steep terrain was asked to stay alert. Anyone living below a steep slope was asked to consider temporary relocation. Landslides also carried a longer-term threat. Once a slope has slid, the remaining soil and rock are often less stable than before. The material at the top of the slide may not yet have moved but is now unsupported. Future heavy rains can trigger secondary slides in the same area. Geologists who surveyed the affected slopes identified several locations where additional movement was likely in the months ahead. The economic impact was immediate. Roads buried by slides had to be cleared. Some required engineering work to stabilize before they could be reopened. Properties damaged by slides had to be assessed for safety before residents could return. Insurance claims for landslide damage are often complicated because some policies cover floods but not earth movement. Many homeowners discovered the gap in their coverage only after the slides had already happened. A construction worker named Daniel was clearing debris from a small slide in the village of Talofafo on Guam. He paused for a moment and looked up at the slope above him. He told a local reporter that the hill had stood there his whole life. He could not remember a single time he had thought of it as dangerous. Now he checked it every morning before he started work, looking for cracks, looking for movement. The storm had changed how he saw the land around him. The next chapter would count the human cost, numbers that mean little until you remember each one was a person. 12 people died in Super Typhoon Sin Laku. The number is small compared to typhoons in less prepared parts of the world. Each death is a complete tragedy. The first victim was a man on Tinian who attempted to secure a piece of metal roofing that had begun to flap loose in the early hours of the storm. The roofing was torn from his hands by the wind and struck him in the head. He was found by his family after the eye passed. Emergency services could not reach the house in time. Communication and roads had been cut off. A second death came in Garapan on Saipan. A woman in her 70s who lived alone refused to leave her home for a public shelter. She had ridden out earlier storms in the same house and believed it would hold. The roof did hold. A flying piece of debris broke through a window and struck her. Neighbors found her the next morning. 2 deaths happened during the storm surge. A father and son were caught in their pickup truck trying to drive away from rising water in the village of Tanapag. The truck was overtaken by the surge before they could reach higher ground. The vehicle was found 3 days later, partially buried in sand half a mile from the road. A construction worker died when scaffolding around a half-finished hotel collapsed during the storm. He had stayed at the site to help secure equipment and could not get out before the wind reached its peak. 3 deaths occurred during the recovery phase. A power line worker was electrocuted while attempting to repair a damaged section of grid before the system had been fully de-energized. A homeowner attempting to cut a fallen tree off her driveway was killed when the chainsaw kicked back. An elderly man with a heart condition died of cardiac arrest while clearing debris from his yard. The remaining 4 deaths were a mix of drowning in floodwaters and injuries from collapsing structures. Each one had its own story. Each one left a family. The death toll could have been much higher. The Marianas Visitors Authority later estimated that more than 15,000 people had taken shelter in designated public buildings during the storm. None of those buildings failed. Structurally, everyone who reached a proper shelter survived the wind and surge. The deaths that did occur clustered in 2 categories: people who tried to ride out the storm in inadequate buildings and people who took risks during the recovery phase before conditions were fully safe. Both categories are addressed in every official preparation guide. Both categories continue to produce victims in every storm. Emergency officials across both Guam and the Mariana Islands held a moment of silence at a public ceremony 2 weeks after the storm. The names were read aloud. Family members were present. Local clergy from several traditions offered prayers. The governor of the Northern Mariana Islands attended in person. The community grief was real and visible. Some of the victims were related to officials, neighbors, fellow workers. The islands are small. Almost everyone knew someone who knew one of the people who died. Memorials began to appear at the locations where deaths had occurred. Flowers were placed on roadsides. Photographs were attached to lampposts. The community marked its losses in the way it knew how. The deaths also produced lessons. After every major typhoon, emergency management offices conduct after-action reviews. The reviews from Sin Laku focused on improving public messaging about post-storm hazards, power line dangers, chainsaw safety, the risks of moving debris in saturated areas. Future storms would benefit from those lessons. Future families would benefit from them too. The next chapter would examine what survived, buildings that held, walls that did not give, lessons in concrete and steel. A storm like Sin Laku is also a brutal test of construction. Every building in the path is a structural experiment. Some pass, some fail. The patterns reveal what works and what does not. The clearest pattern in the Sin Laku damage assessment was the gap between concrete and wood. Reinforced concrete homes built to current codes mostly survived. Older wooden frame homes mostly did not. The difference was visible from any street in the affected areas. A concrete home stood with shutters torn off but walls intact. A wooden home next door was reduced to a foundation slab and a pile of lumber. The Mariana Islands have learned this lesson over decades. After Karen in 1962, devastated wooden housing, building codes shifted toward concrete. After Pamela in 1976 and Paca in 1997, the codes were tightened further. By the time of Mawar in 2023, most newer homes were built to withstand Category 4 winds at minimum, with Category 5 strengthening optional. The result was visible after Sin Laku. Most homes built since 2010 had only minor damage. Most homes built before 1990 had major damage if they were in the eyewall path. The construction era of a building was the single best predictor of its survival. Roofs were the most common failure point even on newer homes. A typhoon-rated roof must be securely attached to the walls below it. If the connections fail, the roof lifts off, and the house quickly fills with rain and debris. Modern hurricane straps and clips are designed to keep the roof tied to the wall plate. Older homes often lacked these and lost their roofs even when the walls held. Windows were another common failure. A window that breaks during a storm allows wind to enter the building. Once inside, the wind pressurizes the structure and pushes outward on the walls and ceilings. A house with broken windows is much more likely to lose its roof than a house with intact windows. Hurricane shutters or impact-resistant glass are the two main defenses. Homes that had either generally survived, homes that had neither generally did not. Garage doors were a particular weak point. Standard residential garage doors are not designed for typhoon force winds. When they fail, the entire garage becomes a wind tunnel, and the rest of the house is at greater risk. Several homes on Saipan lost roofs after garage doors failed first. The pattern was familiar from past storms, but had not been fully addressed in older homes. Commercial buildings showed mixed results. Modern hotels built to international standards mostly came through with minor damage. Older retail buildings, especially those with large display windows, fared poorly. A grocery store in Garapan lost its entire front wall when the windows blew in and the wind pushed against the back wall. The structure was condemned after the storm. Public infrastructure had its own pattern. The hospital on Saipan, built to be a hardened facility, came through the storm without significant damage and remained operational. Schools used as shelters all survived. Government office buildings mostly held. Communication towers were a different story. Several were toppled, taking down cell service for days. The military bases on Guam had been hardened to withstand even a direct Category 5 hit. Anderson Air Force Base flew its aircraft to Hawaii and the mainland before the storm. The remaining ground equipment came through the storm in usable condition. Naval Base Guam moved its ships to sea. Both bases were operational again within days. Trees told their own story. Native vegetation that had evolved with typhoons survived better than imported ornamentals. Local breadfruit and palm trees bent and lost fronds, but mostly stayed standing. Imported trees from drier climates broke and uprooted at higher rates. The lesson for landscapers was clear. Native species are not just culturally appropriate, they are structurally appropriate. The next chapter would examine what was lost when the lights went out. The grid that powers modern island life had a hard story to tell. Modern life on Guam and the Mariana Islands runs on electricity, air conditioning, refrigeration, pumps that move drinking water, medical equipment, internet and phone service. When the grid goes down, all of it goes with it. Within minutes of the eyewall arriving on Saipan, the entire island lost power. The cause was a combination of downed transmission lines, damaged substations, and the safety shutdown of the central power plant. The same pattern played out on Tinian. Guam's grid took heavier damage in the south, but maintained partial service in the north, thanks to better protected lines and the military backup systems. Restoring power after a typhoon is a slow process. The first step is assessing the damage. Crews cannot simply re-energize the system without checking every line and substation for hazards. A live line lying on a wet street can kill anyone who steps on it. A damaged substation can explode if it is energized, while damaged equipment is still in the circuit. The Saipan Utility Company began assessment crews at first light on April 14th. The damage was extensive. Hundreds of poles had snapped. Thousands of feet of line lay in tangles on roads and across yards. Substations had taken water damage from the surge. Transformers had been blown off their mounts in some neighborhoods. Each damaged section had to be isolated, repaired, tested, and brought back online one at a time. The work proceeded village by village. Garapan and Susupe, the most populous areas, came back first. Outlying villages waited longer. Some rural neighborhoods did not have power restored for over 2 weeks. The people in those neighborhoods adapted as best they could. Generators ran day and night where they could be obtained. Fuel for the generators was rationed because deliveries had been disrupted. Food in refrigerators and freezers had to be eaten quickly or thrown out. Many residents lost hundreds of dollars worth of food in the first day. Without air conditioning, indoor temperatures climbed quickly. Tropical heat combined with high humidity made even simple tasks exhausting. Sleeping at night became difficult. Some residents moved into tents in their yards, which were cooler than their homes during the day. Medical equipment that depended on power posed a serious risk. Home oxygen concentrators stopped working without electricity. Refrigerated medications, including insulin, spoiled in the heat. The local hospitals took in patients who could not maintain their care at home. Ambulance services worked overtime, moving people from their homes to facilities with reliable backup power. Communication was another casualty. Most cell towers had backup batteries that lasted 12 to 24 hours. After that, they stopped functioning. Without cell service, families could not check on each other. Workers could not reach employers. Emergency services depended on radio networks that survived, but were stretched thin. The internet went down across most of the affected area. Businesses that depended on internet for transactions could not operate. Online ordering of supplies was impossible. Even credit card payments stopped working at most stores. Cash became the only reliable currency. Banks limited withdrawals due to limited cash on hand. Restoring power was also a logistical challenge. Replacement poles had to be shipped in from off-island. Replacement transformers had to be flown in. Crews from Hawaii and the mainland United States arrived to assist local utilities. The mutual aid agreements between utilities are designed for exactly this kind of disaster. The economic cost of the outage was estimated at millions of dollars. Lost business, spoiled food, damaged equipment, and the labor of restoration all added up. Insurance companies began processing claims, but many of the costs fell directly on residents and businesses without coverage. The next chapter would step back and compare Sin Laku to the storm that had hit the same islands less than 3 years earlier. Mawa in 2023 remained fresh in everyone's memory. In May of 2023, Super Typhoon Mawa passed within 50 miles of Guam at Category 4 strength. The storm was the most powerful to come near the island in decades. It caused widespread damage to homes, businesses, and infrastructure. Repairs took months. Some structures had still not been fully repaired when Sin Laku arrived less than 3 years later. Comparing Mawar and Sin Laku is useful. Both were Category 4 to 5 storms in the same general track. Both produced widespread damage on Guam. Both stressed the same emergency response systems. Mawar's path took it just north of Guam. The eyewall passed close to the northern end of the island, bringing the strongest winds to Andersen Air Force Base and the surrounding villages. Wind gusts reached 140 miles per hour at some military weather stations. The southern end of the island saw less damage. Sinlaku's path took the storm east of Guam, with the eyewall passing over Saipan and Tinian. The winds on Guam itself were significant, but not extreme. Wind gusts at Guam International Airport reached around 115 miles per hour. The damage on Guam was real, but not as severe as Mawar had caused 2.5 years earlier. For Saipan and Tinian, however, Sinlaku was much worse than anything in recent memory. Mawar had not directly impacted those islands. The last direct major typhoon hit on Saipan had been Sudalor in 2015. Sinlaku produced more damage on Saipan than Sudalor had done. The comparison revealed an uncomfortable truth. The Marianas region was being hit by major typhoons more frequently than historical averages suggested. In the 20 years before 2000, the islands averaged one Category 4 or 5 strike every several years. In the 20 years since, the rate had increased. Mawar in 23, Sinlaku in 26, other significant storms in between. The pattern matched what climate models had predicted. Warmer ocean temperatures allow more storms to reach high categories. The total number of tropical cyclones globally has not changed much in recent decades, but the proportion reaching the strongest categories has increased. The Marianas, sitting in a region of consistently warm water, were more exposed to that trend than most places. The recovery from Mawar offered lessons that applied directly to Sinlaku. Building code improvements made after Mawar showed their value during Sinlaku. Homes that had been repaired with Category 5 rated materials survived the second storm. Homes that had been repaired with cheaper materials, or not at all, fared poorly. Emergency response also benefited from Mawar's lessons. Communication protocols had been updated. Shelter capacity had been expanded. Mutual aid agreements with mainland utilities had been strengthened. The Sinlaku response was faster and more organized than the Mawar response had been at the equivalent stage. Insurance coverage was an unresolved issue. After Mawar, many homeowners had been unable to renew their typhoon coverage at affordable rates. Some had dropped coverage entirely. When Sinlaku hit, those uninsured homeowners faced repair costs they could not afford. The cycle of uninsured damage and incomplete recovery was one of the harder problems facing the affected communities. A community leader on Saipan put the situation simply during a public meeting. The storms keep coming, the repairs keep costing more, the insurance keeps getting harder to find. We need help that does not just come and go with the news cycle. The next chapter would place Sinlaku in a wider context. Among storms ever recorded, where does this one rank? The records of tropical cyclones go back about 150 years for some ocean basins. For others, reliable records start only with the satellite era in the early 1960s. For the most precise intensity measurements, the data starts in the early 1980s, when geostationary satellite technology became consistent enough to estimate storm strength reliably from space. Within those records, the list of Category 5 storms that have formed in the months of January through April in the Pacific is short. Yale Climate Connections counted only 10 such storms in the entire historical record. Sinlaku is now on that list. By date, the earliest in any calendar year was Super Typhoon Hester on January 1, 1953. Hester was a powerful storm that affected the Western Pacific in the cold season, when typhoons of that strength are nearly unheard of. The storm's existence was so anomalous that some early records doubted the intensity estimate. modern reanalysis confirmed it. Sinlaku reached its peak on April 12, 2026. By date alone, this places it within the earliest portion of the calendar year for a Category 5 Pacific typhoon. Only Hester from 1953 came earlier. By peak wind speed measured in the early months, Sinlaku at 185 miles per hour ties Hester for second place. The only stronger early season storm was Super Typhoon Surigay in April 2021, which reached 195 miles per hour. Surigay also occurred in mid-April, but did not directly hit any major land area. The list continues with names like Maysak in March of 2015 at 175 miles per hour, Thelma in April of 1956 at 175, Wutip in February of 2019 at 165. Each of these storms was extreme for its time of year. What the list shows is a clustering pattern in recent years. Of the 10 earliest Category 5s ever recorded, 4 occurred in the past 15 years. Surigay in 2021, Wutip in 2019, Maysak in 2015, Sinlaku in 2026. Compared to the previous 50 years, this is a significant increase in early season extreme storms. A statistical analysis published in the journal Nature Geoscience in 2023 examined the trend. The authors concluded that the proportion of tropical cyclones reaching the highest categories had increased over the satellite era at a statistically significant rate. The increase was most pronounced in the western North Pacific, the basin where Sin Laku formed. The analysis attributed the trend largely to ocean temperature increases. Warmer oceans support more rapid intensification. The same favorable conditions that produce Category 5s in summer are now showing up in earlier months as ocean heat content rises overall. Sin Laku is part of that pattern. The storm did not just happen to be strong. It happened to be strong in conditions that climate models had predicted would become more common. The fact that Sin Laku formed in mid-April in the Western Pacific, in waters that were unusually warm for the season, in an atmosphere with unusually low wind shear, was not coincidence. It was the kind of event the warming climate is making more likely. The historical record will continue to be revised as more storms are added to it. The list of early season Category 5s is short today. It is likely to grow in the coming decades. Each new addition will rewrite expectations of what is possible. The next chapter would look at the sole storm that came earlier and stronger. Surigay in 2021 was a remarkable case study in its own right. In April of 2021, Super Typhoon Surigay spun across the Western Pacific. It reached peak winds of 195 miles per hour. Its central pressure dropped to 895 millibars. By every measure, Surigay was the strongest typhoon ever recorded so early in any calendar year. Surigay did not directly hit major populated land. The storm tracked north of the Philippines and east of Japan, eventually losing strength over cooler waters before reaching any major coastline. The damage from Surigay was limited compared to its strength. The storm is studied today as a meteorological case rather than a humanitarian disaster. Sin Laku tracked closer to populated land than Surigay did. The peak winds of 185 miles per hour were just below Surigay's peak. The pressure at peak was a few millibars lower in some estimates. The storm fell short of Surigay as the strongest April typhoon ever recorded, but only by a small margin. The two storms together raise an interesting question. What is the upper limit of tropical cyclone intensity? Is there a ceiling beyond which storms cannot get? The question has been studied for decades. The leading theoretical framework is called potential intensity, developed primarily by Dr. Kerry Emanuel at the Massachusetts Institute of Technology. The framework calculates the maximum wind speed a storm could theoretically reach given the temperature of the ocean below it and the temperature of the air at the top of the troposphere. For most current ocean temperatures, the potential intensity caps out around 200 miles per hour. A storm reaching that limit is rare but not impossible. Hurricane Patricia in the eastern Pacific in 2015 miles per hour, exceeding what potential intensity calculations had suggested was possible. Hurricane Wilma in 2005 reached 185. Typhoon Haiyan in 2013 reached 195. As ocean temperatures rise, the theoretical ceiling rises with them. A 1 degree Celsius increase in surface temperature typically translates to about a 5% increase in potential intensity. Recent decades have seen warming of about 1 degree Celsius. The ceiling has risen accordingly. Surigay and Sinlaku both came close to the current ceiling. They are part of a small but growing club of storms that approach the upper limit of what the atmosphere can produce. As warming continues, the club is likely to grow. Storms that would have been rare a generation ago may become more common in coming decades. There is also a question of what constitutes a category beyond 5. The Saffir-Simpson scale ends at 157 miles per hour. Anything above that is a Category 5 regardless of how much higher the wind speed reaches. Some researchers have proposed adding a Category 6 to acknowledge the difference between a 160 mile per hour storm and a 200 mile per hour storm. The proposals have not been adopted, but the discussion continues. The practical implication is that Category 5 no longer means what it used to mean. A storm hitting at 160 miles per hour produces serious damage. A storm hitting at 190 miles per hour produces damage of a different magnitude entirely. Building codes, evacuation plans, and public messaging may need to evolve to reflect the upper end of the existing category. Sin Laku and Surigay are part of the dataset that will inform those evolutions. The Marianas survived Sin Laku because its building codes had been improved and its emergency response was robust. Less prepared regions hit by storms of similar strength have suffered far worse outcomes. The question of how to protect populations in an era of stronger storms is one of the central problems facing coastal regions worldwide. The next chapter would examine the climate signal directly. Are these storms becoming the new normal? Every powerful tropical cyclone now arrives with the same question attached to it. Was this storm caused by climate change? The honest answer is more complicated than yes or no. No single storm can be definitively attributed to climate change. Tropical cyclones are weather phenomena. They depend on local conditions of ocean temperature, atmospheric moisture, wind shear, and other factors. Any of those factors could be in a favorable configuration with or without long-term warming. What climate science can say is that warming changes the probability of certain storm characteristics. Storms in a warming climate are statistically more likely to reach higher categories. They are more likely to undergo rapid intensification. They are more likely to produce heavy rainfall. They are more likely to occur in extended portions of the year. None of these statements applies to a single storm. All of them apply to the population of storms over time. For Sin Laku specifically, several characteristics fit the climate signal. The storm formed earlier in the year than most Category 5 typhoons in history. The ocean temperatures supporting the storm were unusually warm for April. The rapid intensification rate was unusually high. The rainfall totals were among the heaviest on record for the affected islands. Each of these characteristics is consistent with predictions of how warming would change tropical cyclones. The strongest evidence comes not from any individual storm, but from the pattern of storms over time. Several peer-reviewed studies have documented increases in the proportion of tropical cyclones reaching Categories 4 and 5 over the satellite era. The increases are statistically significant. They are most pronounced in basins with the largest ocean temperature increases. A study published in Proceedings of the National Academy of Sciences examined 50 years of typhoon data in the Western Pacific. The authors found that the average peak intensity of typhoons hitting East and Southeast Asia had increased by about 10% since the 1970s. The increase corresponded closely with the warming of sea surface temperatures in the region. Another study in the journal Nature documented a global increase in the intensification rates of major hurricanes and typhoons. Storms in the most recent 2 decades have intensified faster on average than storms in the previous several decades. The faster intensification gives less warning time to populations in the storm's path. The implications for emergency planning are significant. Forecasters can no longer assume that a tropical storm on Monday will give them several days to prepare for a major typhoon by Friday. Rapid intensification can compress that timeline to a single day or less. Warning systems, evacuation routes, and shelter capacities all need to be designed for shorter notice. The implications for infrastructure are also significant. Buildings designed to withstand a Category 3 storm may face Category 5 conditions more often than the original design assumed. Coastal flood barriers designed for a certain surge height may face higher surges. Drainage systems designed for a certain rainfall rate may face heavier downpours. The implications for insurance markets are already visible. Insurers have raised rates in many tropical regions. Some insurance companies have stopped offering coverage in the most exposed areas. Homeowners face higher premiums and tighter coverage limits. The cost of living in storm-prone regions is rising as a direct result of the climate signal. For the residents of the Marianas, these implications are practical realities. Each storm comes faster than the last warning system was designed for. Each storm requires repairs that are more expensive than the last. Each storm tests the community's ability to recover and prepare for the next one. The next chapter would examine the specific ocean conditions that made Sinlaku possible. The numbers tell their own story. In April of 2026, the surface of the Western Pacific Ocean was warmer than it had been in any April on record. The reading was not just slightly above normal. It was off the chart of historical comparisons. Satellite measurements of sea surface temperature have been consistent and reliable since the early 1980s. The dataset covers more than 4 decades. In all those years, the Western Pacific in April had averaged around 83 to 84 degrees Fahrenheit. In April 2026, the readings averaged closer to 86 degrees. Specific points along Sinlaku's path were measured at over 87. 3 degrees may not sound like much. For tropical cyclones, the difference is enormous. 3 degrees of additional ocean warmth means substantially more available energy for any storm that forms over the affected waters. The threshold for tropical cyclone development is typically 80 degrees. Every degree above that adds fuel. The depth of the warm layer was even more important. Surface temperature alone can be misleading. A thin warm layer over deeper cold water gets quickly stirred up by a passing storm. A deep warm layer keeps feeding the storm even after the surface has been disturbed. Measurements from oceanographic floats deployed by international research programs showed unusually deep warm layers in the Western Pacific in April 2026. The 80-degree water reached down more than 300 feet in some locations. In a typical April, that depth would have been closer to 150 feet. The warm fuel tank was about twice as deep as normal. The cause of the unusual warmth was a combination of factors. Long-term global ocean warming had been adding heat to the Pacific for decades. A weakening La Niña pattern had concentrated warm water in the western basin. Local atmospheric conditions had reduced cloud cover and evaporative cooling, allowing surface heating to dominate. All of these factors aligned to produce the conditions that supported Sinlaku. The implications for hurricane-equivalent storms in other ocean basins are similar. The Atlantic Ocean has also been running warmer than historical norms. The Eastern Pacific has shown similar warming. The Indian Ocean has experienced its own warming trend. Tropical cyclone potential intensity has increased across all of these regions. Researchers at oceanographic institutes have been tracking these trends in real time. Their data feeds into the seasonal forecasts that meteorological agencies produce. The forecasts for the 2026 typhoon season had warned of above-average activity. The early formation and intensity of Sin Laku confirmed the warning. The longer-term projections are more concerning. Climate models project continued ocean warming throughout the 21st century. The amount of warming depends on greenhouse gas emissions over coming decades. Even under aggressive emission reduction scenarios, some additional warming is locked in due to the heat already absorbed by the oceans. Tropical cyclones in coming decades are expected to be on average more intense than tropical cyclones today. The economic implications are significant for tropical regions. Tourism, agriculture, and coastal development all depend on predictable weather. As tropical cyclones become more frequent and more intense, the costs of doing business in tropical regions rise. Insurance, construction standards, infrastructure resilience, and emergency response all become more expensive. For small island nations and territories, the implications are particularly acute. The Marianas have a small economy and a small population. They cannot easily relocate inland or up. They are exposed to whatever the Pacific produces. The frequency and intensity of storms hitting them directly affects their economic viability and their long-term population sustainability. A scientist at the University of Guam summarized the situation in a public lecture after Sin Laku. The ocean is hotter. The storms are stronger. The math is straightforward. The hard part is figuring out how to live with it. The next chapter would look at the broader picture of damage and economic cost. Sin Laku's price tag was climbing. Every typhoon comes with a damage estimate. The number is always preliminary, always incomplete, always rising. For Sin Laku, the initial estimate from the affected jurisdictions came in at over 23 million United States dollars. That number was almost certainly an undercount. Damage estimates after a typhoon include several categories. Direct damage to homes and businesses is the most visible. Damage to public infrastructure, including roads, bridges, utilities, and government buildings, is substantial. Lost economic activity during and after the storm represents another major cost. Long-term effects on tourism, agriculture, and population are harder to measure, but real. For Sin Laku, the initial $23 million estimate covered primarily direct damage to homes and businesses on Saipan and Tinian. The estimate did not yet include full assessments of public infrastructure damage. It did not include lost business revenue. It did not include the cost of emergency response and federal aid. When all categories were eventually added, the total cost was expected to reach several $100 million. The Mariana Islands had a relatively small economy. A storm of this size represents a significant fraction of annual gross product. The recovery would stretch over years. The federal response was significant. The Federal Emergency Management Agency issued disaster declarations for both Guam and the Northern Mariana Islands within days of the storm. The declarations made federal aid available to individuals and to local governments. Aid packages totaling tens of millions of dollars were approved in the weeks that followed. Insurance played a complicated role. The Marianas, like many Pacific territories, had limited private insurance availability. Many homes and small businesses were uninsured or underinsured for typhoon damage. The federal aid filled some of the gap, but not all of it. Many households faced direct out-of-pocket costs that they could not easily absorb. Tourism was hit hard. The Marianas depend significantly on tourist revenue, particularly from East Asian visitors. The hotels and resorts that suffered damage from Sin Laku could not accept guests for weeks or months. Even after physical repairs, the perception of damage in the marketplace caused booking declines that lasted into the following season. Agriculture also took a hit. Farms on Saipan and Tinian suffered crop losses, livestock losses, and damage to barns and equipment. Saltwater from the storm surge contaminated some agricultural land. The recovery for those farms would take seasons. Some farmers would not return to operation at all. The fishing industry suffered significant boat losses. Dozens of small vessels were destroyed or damaged. The harbours themselves required repairs to docks, fuel facilities, and breakwaters. The commercial fishing fleet was reduced for weeks until replacement vessels and repairs could be arranged. The cumulative impact on local employment was substantial. Workers in tourism, agriculture, fishing, and construction all faced reduced or interrupted income. Federal aid programs provided some support. Local government emergency employment programs offered work to those who needed it. The economic disruption affected nearly every household in some way. Comparing Sinlaku's economic impact to past typhoons in the same region shows a consistent pattern. Major storms have been costing more over time. Mawa in 23, Saudalor in 15, Pongsona in 2. Each was the most expensive storm in island history at the time. Each was eventually surpassed by the next major event. The trend is upward. The cost reflects two factors. The storms are becoming stronger on average, producing more damage per event. The exposed assets are also more valuable than in past decades. More homes, more businesses, more infrastructure mean more to be damaged. When a storm hits, the combination drives costs up year after year. The next chapter would examine the strategic dimension. Guam is not just an island. It is one of the most important United States military positions in the Pacific. Guam is a United States territory, but it is also one of the most strategically important pieces of land in the Pacific Ocean. Andersen Air Force Base on the northern end of the island and Naval Base Guam on the western coast together constitute one of the most concentrated military installations in the entire region. Anything that affects Guam affects American military readiness across thousands of miles of ocean. The strategic value of Guam comes from its location. The island sits roughly equidistant between Hawaii, the Philippines, and Japan. Aircraft based at Andersen can reach any major point in the Western Pacific within hours. Ships based at Guam can be at sea in any direction. The island is sometimes called the tip of the spear of American power in the Pacific. When a typhoon threatens Guam, the military response is layered and practiced. Aircraft are flown out of harm's way. Strategic bombers, fighter jets, and surveillance aircraft are relocated to Hawaii, the United States mainland, or other secure bases. Ships are put to sea, where they can navigate around the storm rather than being pinned in port. Personnel are sheltered in hardened buildings. Sensitive equipment is secured in protected facilities. Fuel depots are sealed. Communication systems are switched to backup power. The entire process is rehearsed regularly because typhoons are a frequent feature of life on the island. For Sin Laku, the military preparation began days before the storm arrived. Aircraft began departing Andersen on April 11th. The departures continued through April 12th and into April 13th as the forecast track became clearer. By the time the storm reached its closest approach to Guam, virtually all flyable aircraft had been relocated. The base became a holding pattern of empty hangars and secured equipment. The naval base similarly emptied of ships, submarines, surface vessels, and support ships put to sea. Some headed north toward Japan, some headed east toward open ocean. The strategy was to keep ships in deep water away from the storm's path. The non-military residents of the island faced a different kind of preparation. Civilian flights at Guam International Airport were cancelled for days before and after the storm. Tourists who were on the island had to either find shelter and ride out the storm, or attempt to leave on the last available flights. Most chose to shelter in place. After the storm, the military response shifted to recovery and assistance. Andersen and the naval base both came through with damage that was significant, but did not affect operational capability. Aircraft returned within days. Ships returned to port within a week. The military also provided assistance to civilian recovery efforts. Helicopters delivered supplies to remote villages. Engineering units assisted with road clearance and infrastructure repair. Medical units supplemented local hospitals. The mutual support between military and civilian populations on Guam has a long tradition. Sin Laku was another opportunity to practice it. The strategic implications of typhoons becoming more frequent and more intense are not lost on military planners. A base that is closed for days at a time by storms is a base with reduced strategic value. Hardening the infrastructure to withstand stronger storms is part of long-term planning. The cost of this hardening is significant but considered necessary. A retired admiral spoke at a public forum in the months after Sin Laku. He pointed out that strategic decisions made in Washington and at Pacific Command depend on the assumption that Guam will be available. If the island is increasingly affected by storms, that assumption may need to be re-examined. Alternative basing strategies may need to be considered. The civilian population of Guam, of course, lives with the storms regardless of strategic implications. The island is home, not just a strategic asset. The next chapter would look at how recovery actually works on a remote Pacific island. Recovery from a major typhoon takes years. The visible wreckage is the easiest part to clear. The deeper effects on infrastructure, economy, and community take much longer to address. The first phase of recovery is search and rescue. In the hours after Sinlaku passed, emergency crews on Saipan and Tinian worked to locate everyone who had not yet been accounted for. Most residents had checked in by phone or in person within a few hours. A small number required active search. The search operations continued for several days until everyone was confirmed safe or among the deceased. The second phase is clearing access. Roads have to be opened so emergency vehicles, repair crews, and supply trucks can move. Fallen trees, downed power lines, and debris have to be cut, hauled, or pushed aside. Crews from local public works departments work alongside contractors and volunteers. The work proceeds road by road, neighborhood by neighborhood. The third phase is utility restoration. Power, water, and communications all need to come back online. Each utility has its own timeline. Power is typically the slowest because of the extensive damage to lines and substations. Water can be restored faster once treatment plants have power. Communications often come back as cell tower batteries are recharged or generators are deployed. The fourth phase is shelter for displaced residents. People whose homes were destroyed or rendered uninhabitable need somewhere to live while repairs are made. Public shelters provide initial housing, temporary housing programs from federal agencies. Some residents stay with family or friends. Some stay in damaged homes that have been partially repaired, but are not fully habitable. The fifth phase is rebuilding. Damaged homes are repaired. Destroyed homes are replaced. Businesses reopen. Schools resume normal operations. Each step takes weeks to months. Insurance claims have to be processed. Federal aid has to be applied for and approved. Construction crews have to be hired. Building materials have to be ordered and delivered. For a remote island, the supply chain is the limiting factor. Building materials are not available locally in unlimited quantities. Plywood, lumber, concrete, roofing, and electrical supplies all have to be shipped in from Asia or the United States. The shipping timelines stretch from days to weeks, depending on the source. Prices rise during the post-storm period due to high demand. Skilled labor is also limited. Local construction firms have only so many workers. Mainland firms can send crews to assist, but housing those crews is another challenge. Hotel rooms that would normally house tourists are sometimes used to house construction workers. The economics of recovery shift the local economy in unusual ways. The federal aid process is its own challenge. Applications have to be filed correctly. Documentation has to be scheduled. The process can take months from initial application to receipt of funds. For households without significant savings, the wait can be financially devastating. Mental health is an often overlooked dimension of recovery. Surviving a major storm is traumatic. Losing a home, a business, or a loved one compounds the trauma. Local mental health services, which are typically limited on small islands, are stretched thin during recovery periods. Federal disaster mental health resources help fill the gap, but the need often exceeds the supply. Community resilience is what carries island populations through these recoveries. The Chamorro and Carolinian cultures of the Marianas have deep traditions of mutual support. Extended families help each other rebuild. Neighbors share food, water, and labor. Churches and community organizations coordinate volunteer efforts. The community spirit is real and visible. A recovery worker from a federal agency observed that the islands recover not because of the federal aid, but because of the community structure. The aid helps. The community is what makes it work. The next chapter would look ahead. What does the rest of 2026 look like for the Pacific? Sin Laku formed in early April. The Pacific typhoon season runs through the end of November and beyond. The storm was the first super typhoon of 2026. It would not be the last. Forecasters at the major meteorological agencies use seasonal forecasts to predict overall activity for a typhoon season. The forecasts consider ocean temperatures, atmospheric patterns, and historical data to project the number of storms, the average intensity, and the likely tracks. The forecasts are not exact, but they capture the general expected level of activity. The seasonal forecasts for 2026 had projected above-average activity in the Western Pacific. The unusually warm ocean temperatures were the main driver. The forecasts had specifically warned that early-season storms could be more intense than normal. Sinlaku confirmed the warning. What does Sinlaku tell us about the rest of the season? Several conclusions are reasonable. First, the warm ocean conditions that supported Sinlaku are likely to persist through the summer and fall. Ocean temperatures change slowly. The fuel tank that supported the April storm will continue to support storms through the active months ahead. Forecasters expect continued above-average activity. Second, the rapid intensification capability shown by Sinlaku is likely to be available to other storms throughout the season. The atmospheric conditions of low wind shear and high moisture were supportive in April. Similar conditions are expected to recur during peak season. More rapid intensification events are likely. Third, the locations affected by Sinlaku are not necessarily the locations that will be affected by future storms. The Pacific is a large ocean. Different storms take different tracks. The Philippines, Japan, China, and Vietnam all face significant typhoon risk. So do the Pacific islands of Micronesia, the Marshall Islands, Palau, and other small nations. The rest of the season will see storms affecting different regions. Fourth, the lessons of Sinlaku in terms of forecasting, warning, and emergency response will inform future events. The agencies have learned from the storm. The communities have learned. The next storm will be met by people who have just been through one. Historical seasons that started with an early major storm have generally produced active full seasons. 2021 started with Surigay and went on to produce many additional storms. 2015 started with Maysak and similarly produced a busy year. The early activity is often a signal of broader favorable conditions. The economic implications are also worth considering. An active season means more potential for damage in different countries. Insurance and reinsurance markets will track the season closely. Emergency response agencies will pre-position resources. Aviation and shipping schedules will be affected by storm activity throughout the region. For the Marianas specifically, the rest of the season is uncertain. Statistically, a region that has just been hit by a major storm is no more or less likely to be hit by another in the same season. Each storm follows its own track based on the atmospheric conditions at the time of its development. The community has to remain prepared for the possibility of another major event, even while recovering from Sinlaku. For other regions in the Pacific, the warning is that 2026 is a year to take seriously. The atmospheric setup is favorable for major storms. The early activity has confirmed it. Communities in vulnerable areas should review their preparation plans, check their emergency supplies, and stay informed about developing weather systems. The forecasters at the Joint Typhoon Warning Center and the Japan Meteorological Agency continue to monitor the Western Pacific for new disturbances. Each new system gets evaluated for development potential. Each developing system gets its own forecast and warning bulletins. The work continues regardless of the size of the previous event. The next chapter would zoom out to the longer view. What does the next decade of Pacific storms likely look like? Looking forward beyond a single season, climate scientists and tropical cyclone researchers have published projections for the coming decades. The projections are not certain, but they are based on the best available models and observations. The picture they paint is challenging. The total number of tropical cyclones in the Western Pacific is projected to remain roughly the same or to decrease slightly over coming decades. The reason is that the conditions favorable to storm formation are not expected to change dramatically. Some models actually suggest fewer overall storms. The intensity of those storms, however, is projected to increase. The proportion of storms reaching categories 4 and 5 is expected to grow. The storms that do form will be stronger on average than storms today. The shift toward extreme events is the most consistent finding across climate model projections. Rapid intensification is expected to become more common. The combination of warmer oceans, deeper warm layers, and supportive atmospheric conditions favors the explosive growth that Sin Laku demonstrated. Storms that go from tropical storm to Category 5 in under 3 days are expected to become a more frequent occurrence rather than a rare anomaly. Rainfall from tropical cyclones is expected to increase substantially. Warmer air holds more moisture. Storms in warmer climates produce heavier rain. Inland flooding from typhoons may become a larger contributor to total damage than wind in some events. Storm surge is expected to be amplified by sea level rise. Even storms of similar intensity to past storms will produce higher surges because the baseline sea level has risen. Coastal flooding will reach further inland. Areas that have not historically flooded may begin to flood. Areas that have flooded will flood more deeply. The geographic distribution of storms may shift. Some studies suggest tropical cyclones may migrate slightly poleward as the tropics expand. Regions that have not been historically hit by major storms may face increasing risk. Regions that have been hit may see modest changes in storm frequency, but increased intensity. For Guam and the Mariana Islands, the projections suggest continued exposure to major typhoons. The frequency of Category 4 and 5 hits is expected to increase modestly over coming decades. The intensity of the strongest storms is expected to increase. Building codes, evacuation plans, and infrastructure investments will need to keep pace. For other Pacific Island nations, the projections vary. Some islands may face increased risk. Others may see relatively stable conditions. The smaller and lower elevation islands face existential challenges from sea level rise even apart from individual storm events. The combination of stronger storms and higher seas threatens long-term habitability for some communities. For the larger Asian countries facing the typhoon risk, the projections are similarly mixed. The Philippines, which already experiences many typhoons each year, may see relatively stable storm counts but stronger individual events. Japan, which has been hit by increasingly intense storms in recent years, may see continued strengthening of the trend. China and Vietnam face similar increases in storm intensity. The economic projections are sobering. Studies estimate that climate-related tropical cyclone damage in the Western Pacific could reach hundreds of billions of dollars per year by mid-century in some scenarios. The figures are uncertain, but the direction is consistent. Costs will rise. Adaptation strategies are being developed across the region. Higher building standards, better warning systems, coastal defenses, insurance and reinsurance mechanisms, climate finance for vulnerable countries. The scale of the response needed is large, and the resources available are limited. The gap between need and supply is one of the central challenges facing the region. A researcher at a Pacific Climate Institute summarized the situation. We cannot prevent the storms from coming. We can prepare better, build better, and respond better. Every storm we get through teaches us something. Sinlaku will teach us a lot. The final chapter would look at one more dimension. What can each of us learn from a storm like this? Every typhoon leaves lessons behind. Some are technical, some are practical. Some are personal. The lessons of Super Typhoon Sin Laku will be studied for years. For meteorologists, Sinlaku is a case study in rapid intensification. The storm grew from a tropical depression to a Category 5 super typhoon in under 4 days. The conditions that supported the growth are well documented. The signals that should have triggered earlier alarms are being analyzed. Future forecast models will be calibrated against this event. For emergency managers, Sin Laku is a case study in compressed warning timelines. The storm gave forecasters less time than past systems of similar magnitude to issue warnings and prepare populations. The window from initial concern to landfall was about 3 days. In that window, evacuations had to be planned and executed. Shelters had to be prepared, supplies had to be distributed, and populations had to be informed. The compressed timeline tested every part of the emergency management system. Most parts performed well. Some parts could be improved. For building engineers, Sin Laku is a case study in what works and what does not. Reinforced concrete construction generally survived. Older wood frame construction generally did not. Hurricane straps and impact-resistant windows made a difference. Garage doors and unprotected openings were weak points. The lessons are not new, but they were reinforced by the storm. Future building codes will continue to incorporate them. For climate scientists, Sin Laku is a data point in a longer story. The storm fits the pattern predicted by warming-influenced tropical cyclone projections, earlier formation, faster intensification, higher peak strength, heavier rainfall. Each characteristic aligns with what climate models had been predicting. The storm reinforces confidence in the projections and the urgency of acting on them. For the general public, Sinlaku is a reminder that the world is changing. Storms that would have been historic exceptions in past decades are becoming more frequent. The conditions of the climate we have grown up with cannot be assumed for the children growing up now. Each generation will face different patterns of extreme weather than their parents did. Personal preparation matters. A household with emergency supplies, a clear evacuation plan, and a designated meeting point fares better than one without. The supplies are not exotic: bottled water for several days, non-perishable food, a flashlight with batteries, a radio for emergency broadcasts, a first aid kit, important documents in a waterproof container. The list is short, but each item has saved lives in past storms. Community matters more than supplies. The communities that recover well from major storms are those with strong social networks, neighbors checking on each other, extended families coordinating shelter and resources, religious and civic organizations organizing relief. The structures that exist before the storm determine how well the response works during and after. Information matters. Reliable sources of weather information, clear understanding of the warnings issued by official agencies, awareness of the difference between watches and warnings, between tropical storms and typhoons, between categories 1 and 5. The information is available, the willingness to engage with it is the variable. Long-term planning matters. The decisions made years before a storm hits often determine the outcome. Where homes are built, how they are constructed, what insurance is in place, what infrastructure has been invested in. These decisions cannot be remade in the days before a storm. They have to be made in the calm years between storms. The Marianas have lived with typhoons for thousands of years. The Chamorro and Carolinian peoples have generations of accumulated wisdom about the storms. The modern infrastructure built on top of that wisdom incorporates engineering and meteorology that did not exist a century ago. The combination is what allowed the islands to survive, Sin Laku with as few losses as occurred. Other regions facing tropical cyclone risk can learn from the Marianas. The combination of cultural knowledge, modern engineering, and prepared communities is the foundation of resilience. No region can prevent storms from coming. Every region can be ready when they arrive. Sin Laku has passed. The recovery continues. The lessons will be written into reports, regulations, and personal memories. The next storm is already forming somewhere over warm water. Whether it strikes the Marianas, the Philippines, Japan, or somewhere else, the world that meets it will be a little better prepared because of what Sin Laku taught. The work continues. The watch continues. The Pacific keeps its storms. The people who live around it keep learning to live with them.